In this video, I'll be explaining question 1 of homework 6. So we are given that x and y have joint density function, which is given by the following equation, and it's given that this is valid when mod of x is less than 1 and y mod of y is less than 1, and it is 0 otherwise. So we need to find a so that the above function is a valid joint density function. So to find a, we'll take the integral of fxy dx dy over -1 to 1 for both x and y. This is because from the given question we know that this function is valid when x is between -1 to 1, and similarly for y. Now this integral should be equal to 1 for it to be a valid joint density function. So uh, first we are integrating with respect to y, so it will be when we substitute f of xy as the given equation, it will be so 1 by a can be taken out, and this will be y plus xy square by 2, where y will range from -1 to 1, and so when we try to integrate this, it will come out to be 2, and now we will integrate with respect to x. Again x ranges from -1 to 1, so on solving this will come out to be 4, so it's 4 by equals to 1, which implies that a is equal to 4. Now for the second part, we need to find that if x and y are correlated. So for this we will find the expected value of x and y, xy. So that will be equal to xy times f of xy dx dy, and this will range from -infinity to infinity. Now we are substituting the value of f of xy, which is 1 plus xy by a as given in the question, and we already know from the previous part that a equals to 4, so we'll substitute that. And we also know that x and y, so this is valid only when x and y lie between -1 to 1, so we'll set the range as follows. And on integrating this two equations, we finally get the value as 1 by 9. Now to find the other part, which is expected value of x, so that we can check if e of expected value of x into expected value of y is equal to expected value of x y. For that we need to find the expected value of x. So that can we can find by taking x f of xy, which is this equation, dx dy, and x and y will range from -1 to 1. Now when we try to integrate this, we can find that expected value of x is equal to 0. So now actually we don't need to even calculate expected value of y, because we already can see that expected value of x into expected value of y, whatever it will be, cannot be equal to expected value of x y. So x and y are therefore correlated. For the third part, we need to check that if x and y are independent. So we already know that x and y are correlated, therefore from the previous part we can say that x and y are not independent. Now for the fourth part, we need to find the joint density function of x square and y square. So in order to do that, we'll take u equals to x square, v equals to y square. These will have 4 roots. So now to find f of uv, we will basically take all the four roots, so that will be equal to f of xy for under root u under root v, and similarly for we'll substitute all the four roots, and in the denominator we'll uh, have the Jacobian determinant. Now let's see what the Jacobian will be. So it will be the derivative of these two. So the first will be derivative with respect to x, it will be 2x. Derivative with respect to y will be 0, and derivative with respect to x will be 0, and derivative with respect to y will be 2y. So Jacobian will be equal to 4xy, which is basically 4 under root u under root v. Now when we try to substitute the values into uh, uh, these four equations, then we get the final value as 1 by 4 under root u under root v. And from this we can see that f of uv is basically 1 upon 4 under root u under root v, which is equal to 1 by 2 under root u times 1 upon 2 under root v. So we can see that for the fourth part, which is the fifth part, which is we have to prove x square and y square are independent. For that we can see that since f of uv is equal to f of u times f of v, we can say that x square and y square are independent.